Hello everyone. So today we'd like to discuss Ampere circuital law. Okay. So before getting into the topic, let us first understand or let us get to know what is this all about and what is this law all about and how we can use it actually. Okay. Let's understand this in a step-by-step manner. Ampere circuital law is all about to find the magnetic field due to the current distribution. Okay, but the question is, why do we need to use Ampere circuital law instead of Biot-Savart law? Already we have Biot-Savart law to identify or to find the magnetic field due to a current distribution, right? But still, why do we need this? So listen here, this is very easy. Like, when we are trying to understand the same thing in electrostatics also, like when there is a charge distribution, continuous charge distribution is there, we have a formula to find the net electric field due to that. But when the charge distribution has a symmetry, we use Gauss law to identify the electric field very easily. The same way here also, the Ampere circuital law will help us to identify the magnetic field when there is the symmetry in the current distribution. Yes, this is all about to find the magnetic field when there is a current distribution is symmetry with the help of Ampere circuital law. Got it? Okay, let's get into this topic. You see here, there is a loop which I drawn and there are three vector indications I am showing here. So let's talk about them first. So here I'm mentioning these vector indications as currents I1, I2 and I3. And around them, I drawn an arbitrary imaginary loop which is called as Amperian loop. Amperian loop. So see here, generally what we're going to do here is, if I found any, like if due to some current distribution or due to some current, if I have to find a magnetic field at a particular point, I'm going to draw an imaginary loop so that the particular point will comes on the circumference or else on the surface of the on that line of the loop, so that when I'm integrating it completely with the help of like magnetic field, like closed integral of b dot dl, it is equal to mu naught times of current enclosed in the current enclosed in the loop. So the same thing we'll discuss here. You see this, the loop which I drawn is arbitrary imaginary loop which I'm calling as Ampere loop. In this, the currents are passing through the loop are three, I1, I2 and I3. And here we have taken a little element of length dl which is showing its vector, and due to these three currents we have a magnetic field directionals which is mentioned in blue color vector, and the angle made by both of them is theta. Okay, so what it is now, like what we studied, what I said earlier, similarly we use the Gauss law in electrostatics. E dot dA is equal to q enclosed by epsilon naught. Where it is it here, dA means we are taking as a Gaussian surface and we are taking a small element on the surface and we integrate it. The same way here, we are taking a small element on the loop and we integrated it. And on the loop, when you see here, we have here closed loop, integral closed loop symbol, which means the integration what you're doing with b dot dl is actually on a closed circuit or a closed loop. That is what it indicating, the LHS side. And when it comes to the RHS side, you see in here mu naught and I. Mu naught is indicating permeability of free space, which we know, and I is actually indicating here current, net current or current enclosed by that Ampere loop. So let's discuss about how these are working for this diagram, like how to, for this diagram, what is it formula? Closed integral of b dot dl is equal to mu naught times of I enclosed. I enclosed, we have three currents. Among them, I1 and I2 are in the same direction, whereas I3 opposite direction. You see here that this is how we can identify the magnetic field due to a current distribution with the help of Ampere law, Ampere circuit law. So let's read out the definition and what it is there. Okay. You see here, This law states that line integral of the magnetic field B around any closed circuit is equal to mu naught times the total current I passing through the closed circuit. The formula which we drawn, that is the same here. And the loop on the integral sign means that scalar product B dot dl is to be integrated around a closed loop called an Ampere loop. And the current I enclosed is the net current encircled by the closed loop. Okay. So this is what the Ampere circuital law means. But sir, how do we use it in our numerical sector, it is in the application sector? So let us study about applications of Ampere circuital law. Ampere circuital law. Okay. So here, first when we're studying about Ampere circuital law, I am taking a long straight conducting wire, which means a cylindrical conducting wire, which we see in our regular lives. In our homes, no, we see a copper wire. No, that's imaginary a zoom in process, like in a zoom in size. You see the conducting wire here, and the current is passing through it, and the cross section area of the conducting wire is R. And when you're seeing its cross section view, which means a top view from it, you see in this the blue dot at the center is indicating current is coming out of the page, and the radius R. So with the help of right hand rule, we can find out right hand thumb rule, and you can keep thumb along the direction of current of your right hand and spread your fingers along the radius R. Then you can see your palm is showing a direction. Along the direction of the palm, you have magnetic field there. You have magnetic field there. And along that direction only we used to take the small element vector there. So we have taken a small element on the surface. So okay, let's before getting into the topic, why do we need to take this and what is this purpose? We'll understand first. See, the question is very clear. Magnetic field on surface of a long straight wire with current. So we are interested to find the magnetic field on the surface of a cylindrical wire. So we are taking like this, the top view we are taking like, the cross sectional area. We are considering as an Amperian loop. On this Amperian loop, we have taken a small element which is called dl as along the same direction of the magnetic field. Okay. And we have seen here an arrow mark. This arrow mark is indicating the method of integration, like in which direction we are doing the integration. Got it? Now let's get to the answer, like how to do the integration part and everything. What is the basic formula? We have closed integral of B dot dl is equal to mu naught times of I enclosed, and B is there, and integral of dl will give you, because when you're starting from a point on the circumference of the circle and you will finish complete circle, you will get the circumference. So integration will give you circumference is equal to mu naught times of I encloses. What is the current passing through the complete conductor here? I. So I'm writing I. Let's take in a dot product, so we don't need to write arrow mark there. So here B is equal to mu naught by I 2 pi r. This is the magnetic field. This is the magnetic field on the surface of a solid conducting wire when the current I is passing through it. Okay. Let's get into one more thing. Like in the coming concept or coming question, we're going to study about what if the point which we are taking, like now I am taking the element on the surface. If I'm taking the element somewhere is in the middle, which means between surface and the center, or else somewhere above outside of the surface. So then what is the magnetic field? That's what we're going to study. Okay. Let's clear it. You see here the same wire, but we are taking a cross section, same wire, same radius R. And here, but only one thing, I have taken an element. You see, observe here, there's a little pink color element I have taken, small element, which is mentioned in pink color. The little element I have taken in between center and surface. And from the center, the distance is A. So I have drawn an imaginary circular loop, which is Amperian loop in blue color. And from there, we have element distance is dl, length element dl, and the magnetic field also there. And here I mentioned I dash, which is coming out of the particular elemental loop, which means the complete current in the loop is I, but we are not taking I here. I want to only what is the current passing through that loop. It's always current enclosed by it. So what is the current is outside of it, I don't bother. So we don't need to consider at all. We have to consider only what is the current inside it. Okay. So let's take the basic formula. Closed integral of b dot dl is equal to mu naught times of I enclosed, which means I enclosed here, I'm going to take I dash because that is what it is there. And we know that the loop is having a radius a. So when you do integration, you will get 2 pi a and mu naught times of I dash. So first let's find out I dash. And we all know that what it is, the current passing through the conductor in a uniform cross-sectional area is uniform, which means a constant. So I can take total current I by total area of cross-section is equal to elemental current by elemental cross-sectional area. So I got pi got cancelled and I have I dash is equal to I a square by r square. Now you see here, you guys I dash value. So I'm writing here closed integral of, sorry, don't need to do that. And we have b into 2 pi a is equal to mu naught times of I dash from there. So b into 2 pi a is equal to mu naught times of I a square by r square. You see that a and square got cancelled and you have b is equal to mu naught I a by 2 pi r square. Okay. So now see here radius of the cross section of the conductor wire is constant, 2 pi is constant, mu naught constant, total current passing through the conductor is constant. So which one is varying? A. B is proportional to A here. So you will understand one thing from here, what it is. From center to surface, with respect to distance, magnetic field is directly proportional to it. Whenever the distance increases, magnetic field increases. Whenever the distance decreases, magnetic field decreases when the point is within the center and surface. Okay. So let's, whatever we discussed here, those things we'll study, like we'll read out them as a, let's go with. See here. So first point is indicating us figure shows the cross section of long straight wire of radius r carries that uniformly distributed current I directly out of the page. And the current is uniformly distributed over a cross section of the wire. The magnetic field produced by current is also cylindrical, symmetrical. And thus to find the magnetic field at a point inside the wire, we can use an Ampere loop of radius a as shown in the figure, where now r greater than a. This is what we have discussed, like I've explained you in a mathematical way how we get it. And the process is periodically is written. Okay. Let's understand the relation between B and R in graphical manner. And from the two cases what we studied. Okay, let me clear this. So we are going to, like from the derived relation, we can understand whenever A value is greater than R, B is equal to mu naught I by 2 pi A. Whenever A greater than, like the relation A is less than R, B is B proportional to A greater than B is inversely proportional to. So let's look at this graph. You see that we already discussed this, what it is. When the point is in between center to surface, B is directly proportional to the distance. So we have found that relation here. And once it reaches the surface, from the surface to till whatever the point outside of it, the B's magnetic field is always inversely proportional to the distance from the center of the bird to that point. This is the relation we have got. Okay. So let us discuss one more application or kind of example also you can say about, like, we'll discuss about now hollow cylindrical wire. Now we actually till now we discussed about solid cylindrical wire. Now let us discuss about hollow cylindrical wire. Okay. So see here what we are taking. The figure shows here cross section of long straight hollow cylindrical wire, inner radius A, which is mentioned in blue color, and outer radius B. And there is a current I is passing through it, like out of the page. Now see, here you can observe we have the top view of it, but sir, there are only two circles, but what we have actually here are, what does that mean? So listen here, now the green one at the center which I'm showing as a dot, that is current coming out of the page. And the black circular shape which you see in outer surface cross-section area which is having radius B, and the blue circle is indicating inner surface area cross-section of radius A from the center. And the red color one which I'm mentioning here is nothing but we have taken an imaginary Ampere loop which is having radius R in between A and B. A and B. So now with the help of same Ampere circuital law equation, we're going to find out the magnetic field at different positions of it. Okay, let's take here. What do we have the formula? Closed integral of B dot BL is equal to mu naught I enclosed. And here what we have, B into, if I'm integrating 2 pi R I will be getting, because the radius is R here, and mu naught I enclosed. Okay, so but what is it I enclosed we need to find, because what we have here is I is passing through. Let's find out. I enclosed here. So to that I'm going to take current density. So I by total area. Total area is by outer surface B square minus inner surface A square is equal to I enclosed I'm taking as I dash by outer surface is R square and inner surface is A square. So pi got cancelled, and we have I dash is equal to I into R square minus A square by B square minus A square. So we got it. And when you see here from the formula, B is equal to 2 pi R into mu naught I enclosed, what I am getting, I into R square minus A square by B square minus A square. So I can use here B is equal to mu naught I times of R square minus A square by 2 pi R into B square minus A square. This is what I got as a final magnetic field formula with respect to relation. So here we understand if R is equal to 0, what will happen? The magnetic field. So listen, just anyhow we're going to discuss this later. So the same thing I'll explain now. When the distance, when the R value is from 0 to A, we'll get magnetic field as 0, which means in a halo surface of like from center till A, we have magnetic field is 0. From surface A to surface B will have magnetic field varying with respect to that. And that also we can study. Okay. Let us go to the relation of it and how with respect to position magnetic field is changes. Okay, see here. From R is equal to 0 to A, magnetic field will be 0. When you're keeping R is equal to B, from the formula what you have, B is equal to mu naught I by 2 pi B into R value B square minus A square by again B square minus A square. It will give you 1, so you will get B is equal to mu naught I by 2 pi B when R is equal to B, the same thing. And when R greater than B, then what will happen? Because you don't need to find any current density there, because the total current is passing inside the loop only, directly you get B is equal to mu naught I by 2 pi R. Okay, so that's all, and thank you.